Welcome, sir, and good evening, Bhushan, sir. Hello. May I audible, sir?
Yes, ma'am, you are audible.
You are audible.
Sir's mic is not on, I think so. Sir, make Bhushan, sir, as a co-host. Yeah.
Mr. Sir,
Yes, ma'am. I can unmute myself now. Good evening. Thank you.
Good evening, sir. Yeah. So we will start within 5 minutes, sir.
No problem.
Is that okay?
Yeah. No
Yeah.
problem.
Okay.
Good evening, sir. Myself, Dr. Wagas, HOD NTC. Bhushan, sir.
Yes, good evening, sir.
See the message. Unmute Bhushan, sir. I think you did it. Next, sir.
Yeah.
Ma'am, already hosted.
Oh, okay. Okay. Miss Pallavi, ma'am.
yes, ma'am. Shall we start?
Bhushan, sir, we'll start.
Yes.
Okay. We can.
Good evening, all. Good evening, all. I, Pallavi Patil from ENTC Department of JSPM Rajarshi College of Engineering, Tathode, Pune. I am hosting today's session. So, welcome you all in this 6 days faculty development program, AI and its application in research. For today's session, we have expert Mr. Bhushangarware. Currently, he is working in Google as senior data scientist. He has done his PhD in fingerprint recognition systems from University of Pune. He got gold medal for best PhD thesis. Mr. Bhushangarware has been invited for various talks like accelerating lung cancer diagnosis with artificial intelligence, essentials of machine learning, hands-on workshop on machine learning. So today's session is on advanced track, that is retrieval augmented generation. Now, I kindly request Mr. Bhushangarware to continue with the session. Over to you, sir. Thank you.
Thank you so much for inviting me for this FDP and allowing me to share my thoughts. With that, let me share my screen and let me know if all able to see the screen. I'm sharing my screen. We'll start with the session one. Um, okay, I just have a one screen in front of me. So if anyone of you have a question, I may not be able to see your hand raised, or I may not be able to see your chats when I'm in a slideshow mode. So we can have questions in the end, or if those are super urgent, you can just unmute yourself and chime in. I'm happy to answer those super urgent queries. Can someone give me feedback if my screen is visible? I'm going in a full screen mode now.
Sure, sir.
Uh, is my screen visible? I'm on advanced track.
Yes, sir. Yes.
Okay. Thank you so much. So let's get started. I think we have a back-to-back two sessions today. It's a 6 o'clock, so maybe after 1.5 hours, we will wait and see how much we have covered, and then take a 5 minutes of break and move forward. So advanced RAG, RAG stands for Retrieval Augmentation Generation. If you're familiar with this term, that's fine. Otherwise, I'll definitely cover, what is the meaning of these three words and why it is very important. Before we get started, there is a clear disclaimer from my side. All the views expressed in this presentations are my own and my personal opinions, and they do not represent my employer's view in any way. Okay, with that, let's get started. So today's LLM, that we are seeing, and we call it as a foundation model. Foundation model is, a model which you get from some enterprise companies like uh, OpenAI, Google, Meta, or any other companies, right? So these are the foundation models. I call them as ask me anything model, right? So today if you ask them write a Python function to find nth number of a Fibonacci series, it will give you a code. So literally they are able to ask you anything in the world, right? Now the question is, in order to develop the model which are of a nature called ask me anything, what they want to do is they need to know whole world's knowledge, right? Because you're asking this question and we call it as a zero shot question, like you're not giving any context to those LLMs, you're just firing a question and you expect these foundation models to give you the kind of an answer that you want, right? So in order to do that, these foundation models, they have to be really strong and they need to consume whole world's knowledge into it, right? So when we say that, like how this whole world's knowledge is actually captured in those large language models, and in our part two of this session we're going to actually learn this process of how those foundation models are trained. But for now, for this first session, like imagine this is whole world's information, say few petabytes of the data is there in a maybe on internet, some chunk of an internet. When you train those large language models, for example, if we just take llama 2 model, then all that is 7 to 70 billion parameters, right? What is the size of that 70 billion parameter is 140 GB. So this is something very fascinating, right? So few petabytes of a world information is now compressed in your large language models, and now you can ask anything to this model and you can literally get all the information of the world. So this is super, right? However, there are some limitations. Okay, the biggest limitations that we're gonna discuss is, can you take this 140 GB model and put your on your cell phone and start using it and all that? So at one side, I'm saying this is an amazing work. It's a compression of information and everything is now in a small model. there are some real life limitations of actually using these models. So if you ask me, what is the trend in an industry now, the trend in the industry is like this, like someone who is building bigger and bigger models, people are saying like, okay. But if someone is building a tiny models with equal capability of those models, this is what is the developers needed, right? And some obvious reason like an efficiency, right? So this 140 GB of a model, and this is reasonably middle slice model, this 140 GB model, you can't take it out and put on your cell phone, you can't download it on your laptop and train on your own and all that, right? So it's not efficient, right? You need those smaller tiny models and still want them to work, so they are not efficient. Adaptability. So in order to train this 140 GB model, you need to have a humongous data. There are many foundation models that you can see that when they give you answer, they say that I'm trained on information till this and this, right? So if you want to keep them refresh, retrain on a frequently basis, you need to see the adaptability also. Like if this a model is a huge model, you can't keep it updated on a frequent basis, or even if you could, the cost of updating it is so huge, right? And some effectiveness synthesis. So what point I'm trying to make is the tiny models are actually booming in an industry, right? So how can we decide whether I should have a bigger model or tiny model? So obviously tiny model will save you cost, save you consumption, and the response time and so many factors. But one big thing that is still uh, tech people to the bigger model is an accuracy, right? Because you can't compromise on accuracy. Because my model is small but sometimes it gives you an inaccurate result, nobody will actually take those models, right? So what is a hack? So this rag that I'm going to teach today, it is a smart hack that people have developed, and to solve this trade-off between the size and accuracy concern. So at one side you have this ask me anything model, and this is your big large language model, say 70 billion parameters that you are talking about, and that is giving you an answer. However, what people say is that, do we really need ask me anything model? Now think of your PhD problem, think of some applications that people are using, right? Do just think over it, do we really need ask me anything model and actually need to put all the burden in an LLM to store world's information? Not really, right? You can actually design small application specific, right? So if you have some app in your car, then you can limit like what kind of an answers that model can do, right? Like turn on the radio, tell me the weather outside, turn off the light, change the music, right? So these are application specific. So instead of ask me anything, can you go to ask me anything, ask me specific? I think yes, right? And what people are saying that you can still use smaller models and restrict yourself from ask me anything to ask me specific. On the top of it, you can bring in some external context. So for example, instead of asking zero shot questions like tell me how it is, now what you will do is I'm giving you some context, and now this is my question, now can you give me an answer? It's a still good trade-off, right? So now understand what I'm talking about. So first is called as a retrieval. Retrieval means based on the user query, based on the user query, you will retrieve some relevant content. Now this context is highly relevant to the what query that user has asked, right? So first step is a retrieval. You retrieve the right context based on a user query, then augment it with the question. So to the LLM, you give the question, but augment the context also, and then it will generate the answer. And that's how the RAG come into the picture. It's called as a retrieval augmentation generation, right? And whole today's session we're gonna talk about how this RAG is done and how typically lag is done, and now how what are the trends And as this is an a research specific task, I'm going to discuss so many issues that we face in our day-to-day life, and you can take some inspiration about doing some further research, or coming up some smarter techniques and all that. So this is all about RAG. Okay, so ask me anything. Another issue that these foundation models have is, like, if you work in some of your college, if you see that as per the leave policy of my college, how many sick leaves can I take in 1 year? If you ask this to the foundation model, they will say that, sorry, I cannot answer your question, right? Because what are the policies of your college, these foundation models, they don't know, because they are not trained on that, right? They have not seen your documents, right? So one more need is, like, what if these private documents I want to make available to an LLMs, right? So training your own LLM is a choice, and that we're going to discuss in a part 2 of today's lecture series. But before even moving to training your own LLM, let's understand a hack. Like, you can do a RAG on existing model and you can still achieve a lot of stuff, right? So how this is done, let me explain. So ask me specific, bring an external context. So this context would be policy documents of your college. Question would be how many leaves that I can get. From here, the policy documents will come, and from here you get the answer that you want. So with that, let's see how a typical RAG system is developed. Before even you start querying or using an LLM, there is an offline process. There is a kind of an first step that you have to do is, all the private documents that you have, they must be ingested in a data store. I'm going to explain all this step. What do you mean by ingesting the document into a data store? Right now, you just remember all the policy document, all the PDF and structure, whatever you have, they are by some mechanism now ingested in a database, and this database is now accessible to your LLM. So this is a user who asks the query that comes to an application. What it does is, based on a query, it makes a search in your data store, so that in this data store there could be, say, 10,000 documents, all related to different things in your college and all that. But user is talking about how many leaves I can apply. So based on this query, a search is made. Some relevant documents are retrieved from this data store. So this is retrieval. Query plus retrieval. So they are augmented together. And what will happen is, now this LLM will generate its response. So this process is called as a retrieval process. This process is called as an augmentation, and this process is called as a generation. So that's how the flow will happen. From your query, a search is made. From this search, the relevant docs are augmented with query given to LLM. LLM will generate a response, and this response is sent back to the application and eventually to a end user. So in this case, this LLM could be a as it is foundation model that you have taken, and now you have a liberty to play with a smaller models, on premises and all that stuff, because you don't need like whole world's knowledge, because all the required knowledge that is needed to generate an answer is provided externally, and that's the concept of the RAG. So if you see in this all process, there are two steps. One is an offline process. I'll cut it here. So this process is till the time you create your vector store, and then comes the retrieval phase where user asks the query. From this vector data store, you get the context and generate an answer. So the left hand to this red line, this all is an offline process that you have to do before you actually start using the system. And the first step to that is loading the document chunking, performing embedding, and doing the storage. I'm going to discuss all these things. And in every step, there are some open research problems or blockers, and you may take an inspiration from this discussion to improve the systems, right? And then comes the retrieval, and there is a process of called as an re-ranking, and then comes an answer generation phase where you write your own prompt, will use your own LLM, and eventually generate the answer. So these are the different boxes that we're gonna discuss in today's call. And with that, I'll take a just 1 minute pause. And before I start into details of a loading and chunking, just give me some kind of an feedback, like some thumbs ups and all that, just to make sure I'm making sense, you are with me, and everything is going smooth. Like quick feedback. Are you with me?
Yes, sir.
Perfect. Okay. Yeah. Thank you so much. So I got, thank you. So I'll go back to my screen. I'll go back to the slideshow mode. Cool. So this is what we discussed. So now let's deep dive into all the processes that we discussed. Let's move to an advanced RAG now. So what has changed? Like from typical lag system to an advanced RAG system, what has changed? So what you have to do is, so the newly added boxes are this. So this is a new box that I'm adding. So whatever the query that you have received from a user may not be a best query to do the search. So this is a module where you can do your own research and you can bring your own innovations, and we call it as a query enhancer or called as query enrichment. And from this query to search query, you can introduce a new box, and this is complete freedom for you that what should be there inside this box. But what you want is, you must have seen that my end users may not type a correct query and all that. So it's your responsibility to make sure you expand that query and reach that query, transform that query, and convert that query into search query. So this box number 1 comes under advanced RAG. Now once you make a search, when you get a relevant document, there is a box 2 called re-ranker. And I would like to discuss this step in detail when we reach to that point, like what is an effect of this re-ranker and what innovations that you can bring, and what is an effect of a re-ranker on a final answer. The third box is called as a validator, because you're going to discuss advanced RAG system, maybe an enterprise applications and all that. How can you make sure that generated answer is correct, generated answer is as per my organization policies, generated answer is safe to be present to the user? All that stuff need to be checked and then send the system to the user, right? So these are the 3 additional boxes that you have to add into an existing workflow to convert a simple RAG to a advanced RAG. So let's get started with a first process that we have, and that first process is called as a data ingestion process. How data ingestion process happens, right? Now please understand that first imagine you have a PDF document, or imagine you have a long document, right? So the first step in data ingestion is called as a split into the chunks. So this whole big document is divided into small chunks. Why it is done? Let me explain. So what I'm doing is, if this is my document, what we can do is we split this document into small portions. This process is called as a document chunking. So this is my chunk 1, this is my chunk 2, this is my chunk 3, this is my chunk 4, right? 1, 2, 3, 4. Why document chunking is needed? Because this is a blocker. The embedding model that you have, they have a limitations of the input tokens, okay? And based on what kind of an embedding model that you are using, you have to decide your chunking strategy. For now, just decide this entire document cannot be passed to an embedding model, cannot be passed through this embedding model directly. So you have to come up with some smart strategy of chunking. Okay. So this entire document, it's split into chunk. So this is your chunk 1, chunk 2, chunk 3, and chunk 4. This is a pure text. Okay. So this is in text. When you pass it through an embedding API, for every chunk, you get an embedding. Embedding is what? It's a vector representation of this chunk. So at this stage, for this chunk 1, you have a vector. Okay. This is a vector representation of your chunk 1, then vector representation of your chunk 2. It is called as an embedding 2, and those vectors are then built through an index and put into a vector store. We're going to have a detailed discussion into this. So this is how an ingestion process happens. Okay, taking a document, splitting into chunks, passing every chunk to an API, embedding API, getting those embedding, and then inserting those embeddings into a vector store. This is how a typical data ingestion process happens. Now, let me discuss different chunking strategies for you. And here is how the things will get difficult, and how, it may sound a very straightforward process, but it's not. Okay, so what is the first chunking strategy? The most simplest chunking strategy is called as a fixed size chunking. Fixed size chunking means either you decide on a character count or token count, right? Like after every predefined, it's an hyperparameter in your rack pipeline. Okay, you can say that after every 10,000 characters, I will split the document, or after every 800 characters, I will split the document, right? So something that you have to fix it, right? So this is your document, and after every character count, you are just cutting it together, right? So what is the obvious advantage of doing this? So the obvious advantage of doing this is its simplicity. It's super simple to implement. You don't have to think much. It's just a counting the character and just cutting the document. So it's very simple. It's very efficient. It has a consistency. It doesn't need any computational requirement and all that. So all the advantage that you have are here. But there is a biggest disadvantage. The biggest disadvantage of fixed size chunking is called as a context fragmentation. Now try to understand it. What do you mean by context fragmentation? Now imagine you are ingesting a novel, okay, and in this novel, in this para, somebody has given you some reference of some incidents happen and the name. And in the below para, there is a lot of storytelling and all that, right? Now, what if you cut the document here? So all the information in this is here, but because you cut it, when this chunk is considered, so this is chunk 1 and this is chunk 2, this chunk 2 independently has no meaning, because everything for chunk 2 is explained in a chunk 1. So obviously when you do the retrieval, this chunk 2 is useless and you may lose some information, right? And in a simple term, this is called as a context fragmentation. Because you cut them in the fixed size, the information gets cut. Either there is no reference in the next chunk, or an information is cut half here and half here, and that's why your results may not be good. So what are different techniques that people are doing it? And here is a way for you, right? So here is a way where you can propose, if you're doing a PhD research, if you're doing some small research project, why don't you come up with some new chunking strategies to avoid this fixed size chunking issues? And obviously people are working on it, and it's still an evolving area. There is no right answer for this. Like people are trying to come up with an adaptive approach. They call it as a meaningful chunking, right? So meaningful chunking means what? You actually understand what is going on. This is a para 1, para 2, and then based on the meaning of an context you divide. So let the size of the chunks be different in terms of number of characters, but in every chunk you get entire the meaning of this, right? I have seen some context aware chunking means what? People use some PDF parsers and they understand the structure of a document, right? For example, this is my section, this is my subsection, this is my subsections, and now this is my section 1 and this is my section 2. So here is I have section 2.1 and here I have 2.1.1. Okay, so they understand the structure and make sure that all section 1 goes into chunk, all section this goes into another chunk, right? So they use these parsing techniques. Okay, so what happens is the sky is the limit, right? You can come up with your own innovation, making sure that there is no context fragmentation happening, but all stuff that you do, making sure that what you are doing is you are increasing the complexity. So that complex code you have to write, you have to debug, you have to maintain, and it will take time, right? So that's the trade-off. So semantic chunking, and so how can you make sure that you preserve the meaning? how can you improve the retrieval accuracies and all that stuff. So there are so many stuff that people are trying out, and this is the most favorite one, that I call it as a smart chunking, and it's a hack. Okay. And again, it's not something that you find in the textbooks, but this is something people learned over the period of time and all that, right? So what they do is, the page number, document title, question that chunk can answer, and all that stuff, right? So what people do is, suppose this is my chunk and this is all text here. So what people do is give this chunk to another LLM and ask that LLM, like, can you generate some questions for me based on this chunk? So it generates question 1, 2, 3. And what people do is, all this question 1, 2, and 3, they ingest those questions into this chunk also. What happens with that? So that this is my chunk and these are the questions my chunk answers. So when a user makes a query, you get a direct hit if a user query is very similar to the questions that you have, right? So that's why I say that this is a hack, and sky is the limit. So here you can see that the page numbers, the organization name, then year, these are some additional metadata that is being added to actually the text chunk. For example, when you make a query like, I need the revenue information of Alphabet in 2022. So Alphabet 2022, these keywords will have a good hit, and Q4, okay? So that your retrieval accuracy is really good. So sky's the limit. These are the few examples that people have tried. Make sure that fixed size chunking has a lowest computational overheads. So try with fixed size chunking, see if your results are good. If your results are bad, then think for recursive chunking, smart chunking, context aware chunking, or you can use some kind of an hack. Like, I have seen what people do is, this is my chunk, and they add the summary of the previous chunk, summary of the previous chunk, and summary of the next chunk, making sure that all context is aware. Nobody is stopping you. It's all eventually matters, like, what is the final answer that you are doing. So I'll stop here. Hope you understood. Even in a first step, there are so many ways for you to try out, and there is no right answer. Okay, let's move forward. So here we are. What are the challenges? Incorrect data processing, format discrepancies, incorrect chunking, outdated knowledge. These are all challenges that you have when you actually ingest your data. So what best practices I will recommend for you? Importance for tailored processing means, don't do something because somebody else is doing, right? Tailored to your domain, tailored to type of the documents that you are having, right? Don't copy somebody because they have done it. Your documents are different. Balance between efficiency and accuracy, as I said, you can think of lot of strategies, but they're going to add the complexity in the chunking, and then your results can go on. And very important, and very few people actually take notice to this, is called as a continuous evaluation. So try chunking strategy 1, see what is an output. Change the chunking strategy 2, see the output. Change the chunking strategy 3, see the output. Make sure that your eye is always on an accuracy at the end of your system, like how good my answer is, right? So continuous evaluation is the key. Rather, I just came across a new term people called as evaluation based or evaluation driven development. So initially people used to develop a software, and then somebody used to test it. Now what people say is evaluation driven development. So first you do something and evaluate, then change it and evaluate, and evaluate and evaluate and evaluate, because accuracy is what you want. Okay, let's move forward. What is the next step into this pipeline? The next step into this pipeline is called as an embedding. So let's see, what do you mean by an embedding? This embedding is a very fancy word, and if you remember, it's not something new. How many of you remember this word2vec? This word2vec was developed in 2013. Okay, it's pretty old actually, and I really liked it. And once this word2vec was developed, I think from 2014, people developed RNNs and LSTMs and all that, because this word2vec actually unlocked conversion of unstructured data into a structured data, right? Converting word into a vector representation. And they have a very fancy, a paper from a Google Grain which says that, we have a technique to convert English word into vector representation. But while converting English into math or word into vector, we also carry meaning. And what they say is king, the vector representation of king minus vector representation of man. So king minus man will give you crown, and crown plus woman will give you queen. So very fancy examples that are given. Okay, what they are doing is every word has its own representation. This is how it started in 2020, in 2013, right? And then obviously Bert Quinn in 2017, right after the transformer architecture. And then you have a Bert encoding, and then you have doc to vec, and then node to vec, and eventually now people are using LLM based and all that stuff. What we are doing here is the unstructured data is like, this is all your text. You pass to this embedding model, and what you get is a vector of a numbers, vector representation of this. This is all needed because all the machine learning models, whatever that we do, they can't work on a raw text. You have to convert it into numbers so you can do some math on the top of it, right? So this is how, this is all called as an embedding. So how can you use embeddings? The best step to get started is borrow somebody else's model, right? So use it as an API, any model that you like, pass your image or text, whatever you have, pass it through this model, it will give you a vector representation, right? So if you have a text data, there is a text Geeko model or a multilingual model from Google, and here is what you have, dimensions, input. So this is a token limit, this token limit restricts you to actually chunk the documents, right? So when you choose your embedding model, that is actually putting a binding on how much is your token size that this model can eat and give you a vector representation. So if your document is bigger than this, you have to split it. Okay, and that's why chunking is required. And this is one of the most critical aspect, because if your chunking is bad, your embedding is bad, and if your embedding is bad, your retrieval is bad. If your retrieval is bad, then your answer is bad. Okay, so this is, they all are dependent on each other, right? Multimodal is what you can give image, text, whatever as an input, and they give you vector representation of all this. So that's all about embedding. Now the question is, customize your embedding. Okay, what happens is something like this. Let me tell you. Okay, at one side you can get a ready-made pre-trained embedding models. Okay, so this is your user query. This all documents you have already ingested in your data store. From the user query, an embedding is created, means a vector representation is created. And for all documents that you have, in your data store, they are called as document embedding. And here is a retrieval. Your vector store will find the right match for you, and they will give you the nearest neighbors from this. Now the question is, this is the ready-made embedding model that you have borrowed, using your APIs and all that stuff. What if you say that my accuracy is not good because my embedding model is bad? Because see, I'm working on some very super spatial kind of a data. I'm working on a Sanskrit scripts. How on the earth any foundation embedding model have any idea of how those Sanskrit verses are written and all that stuff, right? Then you may say that no, for my application I have to fine tune this embedding model as per my domain. Then you come into a fine tuning domain, and this is the a part 2 of today's session, where I'm going to talk about LLM fine tuning process and all that. At this time, I'll just give you a high level overview, right? So there is a technique called PEFT, and we will see in depth what is PEFT all about. It's called as a parameter efficient fine tuning, and under that there is an concept where we perform adapter tuning. Okay, adapter tuning means we add some new layer into an existing. So nobody actually changes this LLM fully. So what we do is we take some pre-trained LLM and we add some small network into it, like small portion is added to it. It's called as an adapter model. Then you pass a query to this existing LLM encoder plus adapter section of it, and then you get a vector representation here. Let's call that a query vector. And from here, same, you have a corpus adapter, and then you get a corpus, vectors for all this stuff. Let's call it as a document vectors here, right? So this is how you have to do. So it's a typical supervised training methodology. You have to create a data, like for this query, the nearest document is this. So a query and document pair. So you create, like, this is query, this is Q1. When I give Q1, D1 should have a hit. When I fire query 2, I should have a hit on document 2. By this way, you actually create a supervised training data sets. You do this and you check your nearest neighbors. If you're for a query 1, if you are really getting document 1 or not. If you don't get it, you actually calculate a loss. You go back, you actually perform the back propagation, change the weights of this adapter model. You keep this process on and on and on till the time you feel that your whole as an embedding model is trained or not. Okay, just don't worry. Like, I know this is little bit and and kind of an extra stuff, but most of you gonna happy with the existing embedding model. So this step is for only those who are complaining, saying that my entire RAG pipeline is good, but because my embedding model is bad, I'm not getting good results. So right hand side of the screen is for the people who want to fine tune their own embedding model, and we're gonna have a deep dive into lecture 2 of this series for that. Let's move further. So what we have seen is what is an effect of loading, what is an impact of chunking, and we just saw what do you mean by passing or calling an embedding model. So chunking to embedding is actually converting text into numbers. Okay, so here chunking is a text, and here you got a vector. Now the question is, where are you gonna save those vectors? So those vectors for all the document chunks are stored into a vector store. Now let's understand what do you mean by a vector store. Okay, so vector store. How do they work? Okay, so this is how they work. This is how a typical vector data store look like. So this is a content meant all the documents that you have. Every document is split into chunk. Every chunk is passed through this embedding model, and then you get the vector embedding of this. So all this yellow dots that you are seeing here, so these yellow dots are actually your document chunks. These are all the document chunks that you have. Now user made a query. So this is a query also passed through an embedding model, and imagine this is the vector representation of your query. Now all these are the vectors. Now this is how a vector database is created. You can either design it saying that small n is equal to 2, means give me 2 nearest neighbors, so you get this chunks. Or you can say define the radius r or a distance d and call it as a threshold, saying that d is a threshold. Retrieve all the document chunk under this threshold as th, and retrieve that, right? So this is how a vector database is typically created. So most of you might have used so many traditional databases, right? So understand how vector store is different than traditional data sources. So data type, typically traditional data stores are designed to save the scalar data, but these vector data stores actually save the vector data. You normally save your data in like a row and columns format, but this is multi-dimensional save, like 768, whatever is the dimension of your embedding model. That's how the vector data store is saved. Normally traditional databases are optimized for transactional and analytical tasks, but vector data stores are typically optimized for AI and machine learning kind of task. So typical search method is you type a SQL type of a query on a traditional databases. but these vector data stores work on a principle of similarity search. Similarity search means because in an embedding model, your query goes here, and there are some documents whose embedding is also close to you, means you must be very relevant to each other. So similarity search or nearest neighbor search, approximate nearest neighbor search. That's how these vector databases are available for you. Now the question is there only one data source available, or there are so many data sources, vector data sources are available for me? So before you choose what kind of an vector store I should be taking, let's try to understand the qualities of the vector store, right? So efficient search application. So first thing that you need is like a low latency. Now understand this process. If you remember, all the historical documents are ingested in your vector data store, and then user made a query. Now on that query, this nearest neighbor search is going on, and then you got an answer. So a latency of vector store is one of the biggest concern, because you don't want like user made a query and then just waiting and waiting, because you are actually performing nearest neighbor search in the back, right? So low latency is the biggest requirement of a vector data store. Today you created a POC, you just ingested 10 documents, and then you got your results. But now in a production, instead of this 10, now you have 10 million documents. Now when you increase the number of documents, your latency should remain constant. Now because you have more documents to search for, if your results are not good, if your results are slow, people will not buy it, right? So the biggest quality of a good vector store is a low latency. Okay. Scalability, performance. So their performance should be uh, ideally constant as scale it down, like add more documents into it. Flexibility in data types, like what different data types that it can save. Advanced filtering option, can you actually cut down on it? Like we're going to have a discussion on this called metadata filtering, right? So your data store should give me an option to filter this. And then obviously API and integration, because you want to integrate it in your application, so it should have a good APIs and good support to a lot of other frameworks and all that. So these are the typical the qualities of good vector data store. So there are some open source data store called ChromaDB, uh, FAISS. This is designed by Meta, and there are some commercial vector sources also available called Pinecone, and then you have Vertex Search. So this Vertex Search is in Google's product, which guarantees you all the capabilities that we discussed on the left side. But choice is yours based on how you want to choose. Okay. This you can actually run locally on your machine also, and do some POCs or quick developments. Moving forward, so enough about vector data stores. So as I discussed, this is the offline process. You imagine all the document that you have, you perform loading, you perform chunking, you pass it through an embedding model, you store it in a vector data store. And this is the time when user comes into the picture, and for the first time they are querying to your vector data store. So let's understand what are the different challenges that we face, and what are the different the options that we can have here. Okay. So let's move. As we discussed, the first thing that we're going to do here is called as a query enhancement. Let's understand what do you mean by query enhancement. So first step is called as a query translation. Okay. So this is a query given by your end user. You can use another LLM and perform an operation called rewriting. Rewriting means what? This user query is actually converted into multiple queries. For example, your end user may not write a complete query. Your end user just write few words and all that stuff, right? So what you do is, in order to make sure that you give a right answer to the end user, you perform a rewriting operation, and from one query you create multiple queries out of it. Okay, it is called as a rewriting. Second is called as a decomposition. Some people have an habit of writing a huge essays. Then you said, like, giving some extra garbage in your actual question may confuse your system, right? So that's why you can use an LLM to perform a decomposition operation. You divide this query into subqueries. Like, people may say that, okay, for a business trip, I'm traveling to Singapore, I'm thinking about applying some leaves, but how many sick leaves I can get if I'm going to business leaves, and blah 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 and blah blah blah. Then you have to divide the query about, okay, what is the question, what is our policy for business travel, what is our policy for sick leaves and all that, right? So dividing query into a sub query. Okay, so instead of, so a, a parent query is divided into small sub queries and then ask. In some question, it's like an high level question, like abstraction. So from one query you go to an abstract level and all that. Like, people talk a lot of thing in your query, but eventually you said, okay, you are talking about sick leaves on business travel. Okay, let me give you an answer. So this is all that you have to do. And these gray boxes, as I discussed, uh, gray boxes, we don't have a definite answer like how to do it, but completely open area for you to do exploration and try out in order to get the best answers that you want. So rewrite users query. So you can extract keywords, you can rewrite long queries to short text, fine tune an LLM for rewriting. Or these are some of an examples that I'm talking about. Like, if the user says that compare and contrast Uber and Lyft revenue for me, so you can actually do query decomposition. So user is asking compare and contrast Uber and Lyft revenues for me. Then you can decompose it, saying that first you get done revenue of Uber, then you get revenue of Lyft, get the answers, and then perform this. Okay, this is called as a query decomposition, or query multi step query decomposition. So these are the different examples that you are doing. So if you use llama index, there are some ready-made routines given for you as well. It's not like you have to start from scratch. There you can take some reference words for that. Now, there is a concept called multi-query retrieval, and this is what very important. As I said, an input query may not always capture the sentiments of the data well, right? So this is a user query. You can use a multi-query retrieval. What it does is, from this user query, it creates a generated query 1, generated query 2, generated query 3, and all those 3 queries are passed to the vector data store, and then you get a chunk from query 1, document chunks from query 2, document chunks from query 3. Then you perform deduplication, and this is final context that you pass to the LLM. Okay, and this is called as a multi-query retrieval. If you use LangChain multi-query, it's a framework. Like, uh, you don't have to write this on your own. Okay, you can directly use those modules which are there in Python API from LangChain, and just use it. Okay, so this is one way where people perform query enhancement. There is another concept called rack fusion, and this is very interesting stuff that people have done. So this is a user query. So rack fusion is a library that you can directly use. What they do is, this is a user query. You generate similar queries, and so this is your query 1, query 2, query 3, query 4, and this is an original query. So all those queries are fired parallelly, and the documents are extracted from them. They perform a reciprocal rank fusion, or the process is called as a query re-ranking, and then you actually generate the answer. So this is something new that you are saying, like query re-ranking. So let me explain you that. Long back, like, this is a very known issue. There was a paper, and the name of that paper is called as a lost in the middle. Okay, so name of that paper is called as a lost in the middle. And in that paper, there is a very interesting graph was there. So on a y-axis, they say that the position of the actual answer. Yeah, position of an okay, sorry. Let me erase this. So here on a y-axis, they have the accuracy. Okay, on y-axis they had accuracy, and on an x-axis they have a position. Okay, what do you mean by position? Means if this is a context given to LLM, okay, and if you're counting the tokens from here, so this is token 1, this is token 2, this is token 3, this is token 4, this is say token 8700 and something else. Okay, so this is called as a position of a token, right? And here you have so many English words coming into, this is an overall context that you give LLM. Like this is a context, this is a user query, both is passed to an LLM to generate the answer, like query as well as context. Now, what this paper says is the name of a paper is called as a lost in the middle. Okay, it is called as a lost in the middle. Okay, what they say is they have a very famous graph, and that graph looks something like this. On x-axis you have a position of an answer. So in this, if you ask a query about, okay, what is the revenue of a Google in 2022 quarter 2, and suppose the real answer is here. Okay, so what this indicate is something like this. Like what they're saying is, if the actual answer is, so this is the position 1, which is very early in the document. This is the position 2, which is middle in the document somewhere here, and here this is the position 3, which is late in the document. So what they say is, what this paper says, that lost in the middle paper says that, now imagine how you created this context. This context is this is chunk 1 retrieved from this is chunk 2 retrieved from your retrieval, and this is chunk n that you retrieve. So you concatenate together and get this as a context, right? So what this paper indicates that if the actual answer lies in the middle of the context, then LLMs are not good extracting that answers. Not a particular model, but overall LLMs are not good. However, if the actual answers is very early in the context or very late in the context, then accuracy is good. That's whole the what I would say is that the crux of this paper called lost in the middle. So your answer is lost in the middle of context. Okay, and that's why people are coming up with some techniques called re-ranking. Okay, and I'm gonna discuss a very crude one of the way of re-ranking is something like this. Okay, so what people are doing, this is your chunk 1, this is your chunk 2, and suppose this is your chunk 3. So if there is no re-ranking done, what you will do is you will just concatenate them like this. This is chunk 1, this is chunk 2, and this is chunk 3, and then this is your context. And then you give that context to an LLM. But here you may have an issue of lost in the middle, right? So there are re-ranking strategies. One of the crudest re-ranking strategies that people use is like a keyword search, because this vector search that we discussed so far is nearest neighbor at an embedding level. So it's an contextual search or semantic search based on an embedding vectors. But you can, so at a level 2 you can do keyword search. Keyword search means in your query which words are appearing. So word 1, word 2, word 3, word n. These are the keywords which are present in your query. Those keywords are searched in this chunks, chunks, and chunks. And then you rearrange those chunks. Okay. And then probably you can make it like C3, C1, C2. And these are your re-ranked. These are your re-ranked outputs. That's it. So this is one way of doing it. And then there are model based re-ranking, there are LLM based re-ranking, so many ways. Okay, so this is the process of re-ranking. Now by this way you can take care of this lost in the middle problem. Okay, because you are taking care that mostly your C3 will give the answer. Don't know, this is just an append. There is no guarantee that your answers will improve, but this is the way how people are trying to do that. Let's move to another way where people are doing some advanced retrieval, and it's called as a query routing. As the name suggests, suppose you are working in an office and there are different types of the document. There is a customer data, there is a product data, there are some policy documents and all that. So generally it is not advisable to mix everything into a one data store, right? So you can have a data store 1, data store 2, data store 3, data store n. So different data stores based on the different types of the data. Let user ask the query, and then you use a query selector. This query selector is actually a classifier model, which you can use an LLM for that also. Okay, and the task is given the query, you tell me whether I should go to vector store 1, vector store 2, or vector store 3. It's a classification problem. And then you perform retrieving on that and give your classic LLM for the answer generation. So this vector selector is a new module that you can add, and you can show that after adding this module, now my query routing is good, and that's why my answers are good and all that. This is all about dividing the search space. So this is the all documents that you have, but these are only customer documents, these are only product documents, and these are only some other documents, right? So based on a query, if you understand the customer is asking for this, then you can reroute here. So the search is made only inside this, and your search space is directly becomes 1 by 3. So search space is 1 by 3, so your hits would be good and your answers would be anyway better for that, right? So this is called as an query rerouting. What else people are, so this is one way of doing it, like reroute the query to some other section of it. The exactly opposite of this is something called as an ensemble receiver. Means what? Exactly ulta. So the one query will go to all. So instead of putting a box here as a rerouter, you said, no, I won't put that rerouter. Let my query go to all the data sources that I have. Then let me extract documents from both retrieval, let them combine, and let me re-rank, and let me redo, and then eventually give this final to my LLM. Again, you can use ensemble retrieval or you can use query selector. Choice is yours. These are the different ways people are trying, and as you can see, so many permutation combination, because there is no right answer. It's all that you have to try out. Another way is called as an filtering, and there comes very interesting, is called as an metadata filters. And that's why I said, like, this metadata filter is something very important on your stuff, metadata filtering. And that's why when you select your vectors, when you select your vector store, make sure is it allows you to save the metadata also. Metadata filtering means what? When you index your document, it allows you to save some metadata. So along with the vector of that document, you can save some metadata. Metadata means some additional information, like this is an year and all this, right? So when a user write a, did we implement any new policy in 2021? So then year is 2021. It's called as a metadata filter. So a metadata filter is applied on your retrieval, and only the 2021 documents are passed to the, actually the performing the nearest neighbor search. This is super helpful, and I have seen that after adding metadata filters, the accuracy increases like anything. Okay, now there are two ways by which. One is like user is not aware that metadata filtering is applied, so let user type the raw query. You implement an entity extraction uh, entity extraction model here, and actually extract this 2021 as an year, and then apply that metadata filter and do it. So here user is unaware that a metadata filtering is applied. On other side, on the UI, and I've seen that people are very happy because they want good results. Imagine you built an application and this is your UI. So this is a query. Here, you allow people to type a query. Below to that, you can give actually the drop boxes. Dropbox could be the file type, Dropbox could be the language, Dropbox could be the year, Dropbox could be the country and all that, right? So people will write a query and they actually select what they want. And you must have seen this kind of an user interface on Google search also, right? So on a Google search page, you get something like image search, web search, and some other options, right? So when you click on it, it is an explicit metadata filter is applied, so you'd see only that content. So this kind of an user interface is very helpful, though there is some. So this is how we typically design a system. Like these are kept optional. Like you can give a blind query, but if you give this explicit input on this box, the search query is the search space is divided based on only PDF documents. You will see that the accuracy increases, in a really great way. So I have seen a lot of improvement by doing this metadata filtering, but your vector store that you are choosing should support this functionality. Okay, that's why I recommend to choose a right right vector store. Moving forward, so this is all so far that we saw on a retrieval side of it. Let's move to the answer generation part of it. So first of all, a very important aspect here for answer generation is called as an prompt engineering. So if you see a typical RAG prompt is something like this. That prompt looks like this. First, you have a message which says that, hey, you are a blah, 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 and answer in one line or give a description answer, whatever the application that you have from a bigger context only. So the context, and then you keep context as a placeholder because this context will come from a retrieval that you get, and then query, and this query is also a placeholder that user will type a query, right? So this is how a prompt is written. So your quality of your answer will depend on what kind of a prompt that you have. So, and everybody is now aware of what is an importance of this prompt engineering and all. So all the instruction that you write here determine how good the answer is, and all that stuff. At one side, people are saying, like on a lot of social media, you must have seen that people are claiming that and prompt engineering is like a hot new thing and give you such a big jobs and all that and everything, right? So yeah, you can do that. However, just remember, people have already started to automate this process, right? So amazing paper. I think this came from uh, Google DeepMind latest research. And what they say is that an LLM as an prompt optimizer, right? LLM as a prompt optimizer. You can try that. Means what? Don't worry about, doing a lot of prompt engineering. What you can do is like, you can start with some very basic prompt, and then LLM will take care of, coming up with the best prompt for you. Isn't it great? So you don't have to do prompt engineering, right? You give a base prompt, and this dotted box will actually run some multiple application and can give you the best prompt that you want. Okay, let me tell you what happens. You start with some basic initial prompt, a very basic English prompt that you will write. From this prompt, what you do is a query and prompt input. This you give to an LLM, and you perform this evaluation. Evaluation means how good your answers are, and we're gonna have some a dedicated discussion on how RAG applications are evaluated. So for now, just imagine you just check the accuracy of it. Your accuracy is not, if it is not good, you update it in your prompt store, and then you train it back like LLM based optimization. Like you say that this is what happened. This is how my answer got wrong. So this LLM, a new LLM, will give you a new prompt, and this new prompt you pass it to your LLM, get an answer back, perform an evaluation, get overall accuracy number, give it as a feedback. If that feedback is not good, you come up with a new prompt as a learning. This process goes on and on and on and on. Eventually you'll say that, oh my god, I got the best result that I wanted, and you stop that prompt, and the prompt that you got at this is your final prompt. So this process is called as an prompt optimizer. So you can either spend time you can either spend time on doing manual prompt engineering, or you can actually get started with this prompt optimizer tool. Understand that there is a cost involved here because a lot of LLM calls are going on. So there is no free lunch here. You have to spend some computation on the top of it. But somehow, because as I said, it's an evaluation driven, making sure that it is giving you a new prompt which is giving you the best answer, and that's what you want, right? So somehow it guarantees you the best answer, or at least it is designed to give you a prompt which gives you the best answer. May not give you a guarantee, but it's worth trying, right? So I can try some few manual prompts, and then I'll run through this machine and see how much improvement I'm getting, and move forward. Now, the box that we saw here, it's called as an evaluation, right? So how to evaluate a RAG pipeline? And I love this, though I love this RAG and all that stuff, sometimes it becomes very frustrating. Okay, like you just get frustrated because if you see this pipeline, there are so many places where you can go wrong. Okay, you can make an error while loading or parsing your document. You can make error by doing wrong chunking. There could be an error because your embedding model is not good. You may make an error because your vector store is not retrieving correctly. You make an error because your query expansion is not correct, your prompt is not correct, your LLM is not correct, and that's why your final answer is not correct. Okay, so at every stage of this pipeline, there are so many places where you can make a lot of errors, and that's why I haven't come up across any pipeline where there are multiple places where you can go wrong. So evaluation of RAG is really, really, really challenging. Okay, but you can't do everything, right? So there are two places, where people actually do the testing. So let's understand how RAG pipelines are evaluated. This is how the structure is. User query went to a vector database. You got the retrieve context. This is an LLM, and this is a response. So this is the simplest diagram for a RAG that you can see. So what you can do is at the end of the RAG pipeline, I don't care what you have done in the back. I'll just check your final response. And this is an evaluator. And evaluator will say that I have ground truth answers. I don't care what you have, like what is your final response and is it same with what I want? And I'll just evaluate at the end considering all your RAG as a so this is your RAG, the entire pipeline, and saying that this RAG as a black box. this is the query I gave to you, this is the response that you have given, but I have a ground truth, and I'll compare these two, whether they are correct or whether they are wrong. That's it. This is one evaluation. Where the problem is your job. You figure out. I want a final answer. Okay, so there is one more step which I like is, you know, your your response would be definitely wrong if your retrieval is wrong. So people say that your RAG is as good as how good your retrieval is, right? Because it has, like, it's an error propagation, right? If you get a wrong document, if you get a wrong documents at a first place, there is no way this LLM will do. No matter how much prompt engineering that you have done, it's like a typical garbage in, garbage out. Yes or no? So this is another place where people test it, like, at least my retrievals is giving me right document. If retrieval is not getting, there is no point giving anything to LLM or seeing what the response is coming. So one strategy that people use it, they actually create a ground truth context. Ground truth context means, this is their document. So they actually take this para as a context and says that, query and context, they create this ground truth table, like, for this query my answer should definitely come from this section of a document, and then check if your vector database is actually giving you that context or not. So these are the two areas, because as I mentioned, this entire pipeline, you can't test it everything. So at a retrieval stage, one testing is done, and at a final answer level, one testing is done. Again, this is the what I would say, that this is the trade-off, or this is what, suitable strategy that people are using. But I'm not restricting you to do that. You may come up with, some evaluation strategy to check, like saying that this is my research and this is my library, which will test you the chunking strategy, which will test you if your embedding API is doing good or not, and all that. As I said, sky is the limit. This section is for the people who are doing research. I'm just giving you lot of problems where, you can come up with some solutions. So spectrum of evaluation strategy. So eyeballing, I'll just quickly see, which one is correct, or I can actually do manual evaluation. So if I do manual evaluation, checking every response and all that, obviously the reliability is good. But if I just do eyeballing, the speed is good. But, as you understood, reliability, you need it high, you can do manually, but how much you can do manually? So there is always a trade-off between reliability and speed. So the best option that people will say that I'll use LLMs for that, which will give me a good trade-off between reliability and speed. Okay, so there are some LLM based evaluators. So evaluating retrievals, if you want to evaluate the retrieval, this is the query, so for a given user query, these are the retrieve chunks, and ground truth chunks are also available, and then you compare them by using LLMs. So these are the different metrics that people use to compare how good the retrieval is. It's called as an hit rate or precision, reciprocal ranking, normalized discounted cumulative gain, NDCG score, recall, and map. So if you see this retrieval is as good as, it's a search problem, isn't it? It's a search problem. Like for a given query, you search the right content. So hit rate or precision and recall is very frequently used by the people. Another way is, as I said, a RAG system as a black box. You gave a query, you got the generated answer, and you have a ground truth answer, so you can directly compare them. So these are some of the metrics that people use, called answer correctness, answer semantic similarity, context precision, context recall. And these are, when there is no ground truth, you can still compare how good the answer is, like how goodness, how helpful the answer is, how relevant the answer is to my question, are there any hallucination, how faithful the answer is, and all that. And as I can see, this is still evolving. Okay, people are come up with their own idea, so it's a good, could be a good research problem that you can say that, hey, I come up with a new metric and which is more usable compared to all that stuff. So what is available today in the market? So there are two frameworks which are open source. One is called Ragas, especially designed to test the RAG pipelines, and there is a deep eval. This is came up from Microsoft Research and open source evaluation framework. And then you have some services like Vertex AI, Rapid Eval, and all that, but those are not open source, and you have to pay to use those services via API calls and all that stuff. But these are the some of them you can actually use on your thing. Again, these frameworks are open source, but in the back you still need to make an LLM call. So these are also LLM based evaluators, as we discussed on this slides. These are LLM based evaluator, not human based evaluator. So reliability is still questionable. There are still areas where you see that, hey, as a human, I don't see this is a correct answer, but this framework are saying that answer is correct. So there is a scope for research to come up with some frameworks like this. Further enhancement. So where we are, so we are on the verge of concluding this part one of a series, right? So if you are developing this RAG pipeline, what should you try first? So you start with a simple RAG. What should you try first? If your results are not good, you think for some better parsers, work on some chunk strategies, work on some metadata filter, work on some query rewriting. These are some very simple hacks that you can do. Those are very easy to implement, low latency. There is no much cost involved into this. If this all is not working out, then you can work for an advanced retrieval. You can think of some rewriting, hierarchical retrieving. You can think for some parent document chunking and all that stuff. Or you can, in the last, you can go for fine tuning. Fine tuning, saying that this embedding model, ready-made embedding model is not good. My LLM is not good, so let me fine tune that and all that. So as you can go from left to right, they are hard to implement. They will increase the latency because it's custom. They will increase the cost. So be very careful when you move to the right side of this domain. So these are the three areas where you can see, where you are seeing those gear size are the places where you can actually, so this embedding model you can fine tune, this re-ranking model you can fine tune, or this answer LLM that you can fine tune. How to do fine tuning is the part 2 of the today's session, where I'm gonna teach you actually the process of tuning an LLM. So even if you do fine tuning, in many cases you will see that my answers are not good. And then what you can do is some very super special thing. It's called as an agentic behavior, or multi-document agent, or rerouting. So from advanced RAG you can move to the agentic RAG. So what is the agentic RAG? So this is called as an AI agent, and there is still an LLM, and it has some reasoning and planning. It has an access to an environment. It has access to your vector data store. Additionally, it has access to some external tools as well. Okay. So what an AI agent look like? So AI agent is something like this, which has a reasoning loop, which has its own brain to take a call based on a user query. Should I use my vector data store to answer an answer, or should I use this tool and make a Google search an API and get an answer? All that stuff is done, right? So under the tool, you can use some functions, some data store, some extension, and under the reasoning loop, this reasoning loop, which actually could be a rule based, could be another ML algorithm, or some probabilistic algorithms will come into picture. So this is how an agentic RAG system at a high level looks like. Okay, this is a user query. This, instead of going it to a directly to an LLM, it go to an agent. This agent will understand it, do query planning, do some reflection, some reasoning, and then take a call like, okay, based on a query, it says that, hey, I can answer it by RAG. So it goes to a lag pipeline and give an answer. Or in some cases, it says that, hey, I think my RAG is not giving an answer. Let me go back and do the Google search. So tool is like Google search. It can go to weather API. It can go to maps API. It can go to your databases and API and eventually generate an answer. It's called as an agent. Okay. And then what else, where the things are moving from this, like, then if it is an agent, then the world going to a multi-agent system. Like, so this is one agent which can talk to the tools, which can talk to the RAG, However, this one agent can talk to an agent 1, agent 2, and agent 3, right? So it's called as a multi-agent rack system. And I don't know after this, like where it is going, right? So it's a multi stuff. So that's how, an advanced RAG is going on. So if you see how the evaluation is happening, so traditional RAG is like this. You have a query, you perform nearest neighbor search on a retrieval, you got the context, then you generated an answer. So from traditional RAG to advanced RAG, you make the changes like this new boxes are adding query transformation, re-ranking and filtering. So you call it an advanced RAG. From advanced RAG, now you're going to an agentic RAG where you are doing task planning additionally, and then you are doing dynamic context management, knowing the user, knowing their history, having the memory. This all improves the answers that you have. So this is an agentic RAG. So that's it on the part 1 of this series. I had a long monologue. Hope you find it interesting. We can take 5 minutes for Q&A on this session. So yeah, I'm happy to answer if there are any queries.
Participants can unmute themselves and ask questions.
Good evening, sir.
Good evening.
Sir, I have a question that suppose I just want to work with some satellite images, like for my deep learning concept, or you can say that for my thesis. So may I know, like, is there any kind of models that you can suggest for that or something like, sir?
This becomes like a very what I would say is super special questions related to the problem. Maybe we can take it offline. I have shared my email ID. You can write it to me. Not related to probably the RAG pipeline that we discussed today,
Okay,
but
okay.
people are doing, like, if I want to tweak your question and bring it to the topic that we had is today, like, if you want to build some application, like, user come up with some kind of an imaginary at a first place, and then thinking about some similar images in the past and all that, then it's kind of an image to image search kind of an application that you can still build using RAG philosophy. Like, imagine you have all the images in the back, you pass it through a multimodal model, create a vector out of it and save it into a vector data store, and then user come up with its own new image. Then you pass that image, create an embedding out of it, and then do the nearest neighbor search and give them back some relevant results and on the top of it. So those kind of an applications you can still build using this RAG pipeline on images. So here the model that you have to use is, instead of text embedding, you can use multimodal embedding. But because you are working on satellite imaginary, right? Uh, there probably you will have to use some specialized embedding models, or maybe you may have to come up with your custom embedding model based kind of a data that you have, because general models that are available, those would be may not be helpful, because you're working on some super special domain. In a part 2 we're going to discuss this fine tuning aspects of it.
Sure, sir. Thank you so much, sir. Thank you.
Any other questions?